And now for the LCROSS portion of the payload, Dan Andrews, the LCROSS project manager from the NASA Ames Research Center at Moffett Field in California. Dan?
Thank you, George. It's a pleasure to be here talking about this very exciting mission. I'm going to start by telling you the end of the story, and then I'll go back to the beginning. If you could roll the video, we're going to be doing some lunar prospecting, if you will, excavation style. This is how our mission is going to end, actually twice, with an impact on within a South Pole polar crater. And the reason that we're doing that is we're going very tactically in to discover if there is indeed water ice present in the bottom of those permanently shadowed craters. The reason that we believe there could be is there's strong indications from previous missions, two notable ones being Clementine and Lunar Prospector, that showed elevated hydrogen in those areas, and that could be an indication of a fair amount of water. So we're going to go in and excavate it and see if that's the case. If we show the next video, I give you an overview of the mission. First, we start with an ESPA ring. That's that circular yellow ring that you see there. What that is a secondary payload adapter. And we're a very low-cost mission, and so what we've done is turn that into a spacecraft. You can see with our partner Northrop Grumman, we actually have built a spacecraft where we put, a solar array on one of the ports, we put batteries on another, and then the Ames developed payloads on another. So you've now seen a launch video. This is the Atlas V. And if you look closely, there's LRO on top, LCROSS in the middle, and then the Centaur. And here's a representation of LRO now separating, going about its mission. So at this point, LRO is now, as you've heard from Craig, off and performing its mission, its commissioning orbits, and so forth, which leaves us with LCROSS. LCROSS continues towards the moon and does a swing by and never enters a lunar orbit, actually enters an Earth polar orbit. See that represented here. And the whole point is to position ourselves so roughly 100 days or so later, we go into a South Pole permanently shadowed crater. So what we're doing on the final descent is trimming out our positioning so that the now cleaned up and spent Centaur, that you heard Vern talk about, is ready to be dropped in. We don't shoot it in, we just let go of it and let gravity do its thing, lunar gravity. So we position the stack so that Centaur is pointing in. We trim out with the shepherding spacecraft our orientation, and then you'll see in a moment the separation occur. Once that separation occurs, both of these, the Centaur and the spacecraft, are being pulled in, ultimately for an impact velocity that'll be 5,600 miles an hour. The problem is we need to be able to have that shepherding spacecraft see the impact. So what we do is slow down, burn some propellant, and decelerate our inevitable acceleration into the moon to buy us time between the two impacts, about 4 minutes. So here you see a representation of the Centaur going into a permanently shadowed crater. And then the shepherding spacecraft flying in behind it. Here's an over-the-shoulder view, taking measurements live, what we call bent pipe, sending them back to Earth live, taking all the different measurements of the lunar regolith characteristics, looking for water vapor, looking for water ice itself, and so forth, until inevitably the shepherding spacecraft sees the same fate. That's why we don't have onboard storage. It's gone now. So this is a very exciting mission and a very inexpensive one, and so we're happy that LCROSS will be a smashing success.
I understand the scientific data that comes from LCROSS is important, but does it have any bearing or importance on the next phase of exploration, as you were talking about? I understand the LRO does, but does LCROSS also have an impact on or data that's important for the exploration mission?
Sure. I would say in our current architecture, we're not counting on the water to be there to actually enable it. But it's certainly intriguing, and to know that there might be water deposits in places where you could go in and live off the land versus bringing that water from Earth. I believe we use something called a gear ratio. For every pound you want to put on the moon, it's 20 pounds on the launch vehicle side launching off. So weight is obviously very important. To not have to carry that water up would be a great thing.
Chris Gephardt with NASASpaceflight.com again. You mentioned the further to the right you go, you start to lose the visibility on the eastern and the mid portions of the U.S. for LCROSS. Is visibility from the U.S. a mandate for this mission, or will you get all the information you need from the LCROSS satellite itself?
So I'll take a stab at that. LCROSS shepherding spacecraft is designed to get everything it needs with no assistance from Earth. Okay, what Earth gets you is a couple different things. One is that it gets you robust additional measurements. You could, if things were favorable, have millions of eyes, including a strong amateur community, looking at this thing. And when you gather all that data, you have a very robust, multi-point of view collection of data. So it's great for engaging the public scientifically, and then also just from a inspiring future generations. This could be very participatory if the conditions allow for it. With a 10 to 12 inch telescope, if you're in a favorably dark area of the country, you should be able to actually witness the impact. So it would be very exciting and engaging for the public, even beyond a scientific value.
There was a reference in a prior briefing to the volume of water ice that, if it's there at all, and if it's as much as you think it could be. Could you just give us, or repeat, or give us a more specific estimate of how much that might be if it turns out to be there?
So I'm at the front here. I'm going to defer to the science briefing to give you, which will be tomorrow, to give you the details. But this is the conundrum about this measurement. There is data out there which could show that it's potentially ice rinks. There's data out there that shows it could be blocky. There's data out there that could support the fact that there may not be water ice there, and so that illustrates the importance of this mission. Let's go see what it is, and if it is present, that could have very strong benefit for future sorties and habitation for a number of different reasons.
Was there any significance to the timing of these satellites flying now? Was it just that they're ready to go, why not, or was there any other reason behind it?
Well, I think once we made the decision to build the satellites, we want to get the information as soon as we can, because it informs our architecture, it informs where we want to land. If we were to find water, I mentioned that it's not a current requirement in the architecture, but you could imagine the technologies that might go into the ways to farm that water, and so you'd want to get started on those kind of things. So from that perspective, I would say as soon as possible.
Why did you choose Earth polar orbit to the impact? Why do you spend 4 months or 3 months in orbit to waiting for the impact?
So, somewhat complicated answer, just in that there's a number of reasons. The first thing is we are not the first lunar impactor, of course, impacting the moon to do science and to study what comes up, and the nature of the regolith has gone on since before I was born, frankly. What's different about LCROSS is that it is tactically employed as an impactor. So everything that we do with our mission design is around maximizing the value of the impact. Even Lunar Prospector ultimately became an impactor. That wasn't its purpose, but at the end of its life it was going to hit the surface. And so the Lunar Prospector folks did some clever things to try to maximize the return that they could get from an impact by Lunar Prospector. Turned out to be of questionable value, but it was a valiant, last benefit. For LCROSS, by entering an Earth orbit, we get a very steep impact angle in the permanently shadowed crater. And in this current block that we're in, it's actually about as good as we've ever seen it. It's up above 80 degrees impact angle. And that makes for a very favorable ejecta plume that would come out. You're almost at a 90-degree angle, which kicks more material up into the sunlight to allow us, as it's subliming the ice if it's there, to measure it and so forth. And then the other part of it is, because we're designed to be an impactor, we carry more mass. For example, the energy of our impact will be 200 times larger than that of Lunar Prospector, which was a much smaller spacecraft and had a much lower impact angle. I believe it was on the order of 20 degrees. So we're specifically designed to be an impactor, and that's the reason for the mission design.
LRO is a focused set of measurements that will do the best possible attempt at determining the characteristics of the lunar surface, particularly at the poles, with remote sensing instruments from orbit. However, to really understand the water content of the surface, you would like to land there and touch the surface and find out what the characteristics are in detail. We're fortunate that LRO will carry to the moon a companion mission, LCROSS, that will literally touch the surface in a very dramatic way, and LCROSS will seek water on the moon. And Tony will tell you about LCROSS.
Thank you, Rich. Thank you, everybody. It's good to be here today. As Rich mentioned, a key interest to NASA and the broader community in general are resources at the poles of the moon. And we have two missions early on that nearly more than a decade ago now, two small innovative missions, Clementine and Lunar Prospector, that gave us the first hints or data that there could be water ice at the poles of the moon. And in that spirit, LCROSS, a small fast-track mission, is going back with LRO, as Rich mentioned, to search out for the source of the measured hydrogen at the poles. And to do that, it will use the upper stage of the rocket that pushes LRO and LCROSS to the moon, the Centaur rocket, as an impactor, very much in the same spirit as the Deep Impact mission to Temple 1 comet. I'm going to show you some video that shows the distribution of measured hydrogen at the poles, how we're going to use an impact to make a measurement of what's in these very dark craters, and then describe some of the instrumentation on the LCROSS spacecraft, which will observe the impact up close and personal, and also describe some of the other observatories and assets that will be making measurements along with us. So if we could start the video, I'll walk through it with you all. Lunar Prospector measured neutrons at the moon, just like the LEND instrument will on LRO, but to a poorer resolution than LEND will. And what it found was concentrations of hydrogen at the poles. It only measured hydrogen, so we really don't know if it's in the form of water ice or some other form of hydrogen-bearing compound. As Rich mentioned, there are these permanently shadowed craters at the poles, and this is the same graphic that Rich showed. The blue areas are these craters that could be 200 degrees below 0 centigrade, very cold, excellent cold traps, could hold a variety of different volatiles. Well, how do you get something that's been in the dark for maybe 1 billion or 2 billion years out to study it? We use a Centaur, a 2,300 kilogram dead weight after it's done propelling us to the moon, as an impactor. This next video shows one of our co-investigators, Peter Schultz, simulating the impact at the NASA Ames vertical gun. This shows how the impact will look from the side if you were so fortunate to be standing on the moon watching it. And what you see is ejecta coming up out of the dark crater and into sunlight. We call that the sunrise of the ejecta, and it's really lifting material up into sunlight for the first time in 1 billion years so we can actually look at it. This next video shows the shepherding spacecraft. That's the LCROSS spacecraft that actually tugs the Centaur around after launch and eventually targets it into the moon. Here it shows after we've released the Centaur, it is out ahead of us, impacting the moon. We follow it in with this spacecraft, never further than 600 kilometers away from the impact and closing fast, about 2.5 kilometers per second, making observations all the way in until we become an impactor ourselves. This shepherding spacecraft carries 9 instruments on board. They're shown here in what we call the pod, the payload observation deck. And I'll walk briefly through each of the instruments. The 2 workhorses on for measuring water ice are the near-infrared spectrometers. We have 2 of them, one side looking at the sun, one looking down at the impact. We have an ultraviolet visible spectrometer that's also looking for various compositional signatures in the ejecta cloud. We have two thermal cameras that will measure the temperatures at two different wavelengths of the ejecta cloud and the flash. We have a three-color camera also. This is a context camera. It allows us just to understand exactly where we went and where we hit. We have then two near-infrared cameras. These two near-infrared cameras are sensitive to water ice and composition. They're at two different wavelengths, and they provide context for the near-infrared spectrometers. And then we have a unique instrument developed by NASA Ames just to measure the flash of the impact, the total luminescence photometer. It's actually the first instrument that will give us some kind of clue as to the presence of volatiles in a crater. LCROSS is not the only observatory that will be looking at this. We have observatories all around the world that will be looking. We have observatories in space that will be looking, and we have observatories at the moon that will be looking. This is truly unique. I don't think there's ever been a mission that's had so many assets looking at the same time since maybe the Shoemaker-Levy comet impact at Jupiter. This last graphic showed all the various observatories that we have. We have the primary observatories over in Hawaii, because the impact will be timed to occur, so that's in good viewing over Hawaii. We have all the major observatories online and ready to observe. We have assets in the western coast of the United States, in California, Arizona, and New Mexico that will be observing as well. We have also assets in South Korea and actually South Africa that will be looking before and after the impact. So we have a very broad Earth-based campaign. We also have Earth observing assets, including the Hubble Space Telescope, newly refurbished, which was critical to actually make these measurements, that will be looking. And we have a European spacecraft called Odin that will be looking with a microwave radiometer. And then very uniquely, we have LRO, of course, in orbit that will be providing a great bit of benefit to LCROSS by pre-mapping the craters before we impact, and then being able to observe them as the actual impact occurs, and then of course characterizing the impact sites in incredible precision, as was described by Rich and Mike. The Chandrayaan spacecraft, the Indian spacecraft that is there too, we're working with them closely, and they hope to make observations as well. So we have many eyes looking in a variety of different ways, and this really demonstrates the robustness of this small LCROSS mission. We will get several unique looks at the ejecta cloud, the flash, and the remnant crater that will help us to understand better the source of the hydrogen signature that we've seen at the poles of the moon. So with that, we're excited to get going and explore the moon in a way that never has been done before.
We also have education and public outreach programs for the entire mission and the individual instruments. And regarding the camera, the LROC experiment team is working to have a public website where actually individuals can propose a target of their own that they would like to get images from. We think this would be very appealing to educators and students. There's a similar program that's operated like that for Mars, and we look forward to that as a way to engage the public and inspire the next generation.
And on LCROSS, we have a shorter mission, of course, but and it's a real-time mission. Everything on LCROSS is from flying the spacecraft to the impact is now. There's no repeat. So in that vein, what we are actually doing to engage the public is streaming our camera video live to the web. So the entire community worldwide can see what we see in the Science Operations Center at the same moment, more or less, as when we see it. Also, if we're fortunate enough to have viewing, if you're in an area where you do have viewing, a modest telescope, 10 or 12 inches, you should be able to observe the flash and ejecta cloud, depending on, of course, on weather. So the LCROSS is trying to engage the community in a variety of ways, also through getting amateur astronomers who have helped the professional astronomers understand the illumination of the moon and how to find a crater on the moon. If you haven't looked at the moon before and you're asked, go find a crater with your 10-meter telescope, it's a hard thing to do. So we've actually, for the last year, worked with amateur astronomers who are very good at this. They've actually helped the professionals develop a whole means of using guide craters instead of guide stars to point these very large telescopes. And so we've already actually engaged a large portion of the public for help in our mission. And then we'll be hopefully contributing to the real-time sense of the mission in a couple different ways as the LCROSS mission unfolds.
Thank you. This is Tariq Malik from Space.com and Spaces. I think I have one and a follow-up. And my first one actually, maybe for all three of you up there. I know this mission was delayed a while, and I'm just kind of curious how it feels personally to you and maybe to your team to kind of be at a point now where, despite those delays since October of last year, you're ready to fly and you're ready to start your mission.
Well, one of the things that we all know about the developing missions for flight, and that is that it's a tough job, and we know that we can't always be able to launch exactly when we want to, and most of the time, in this case, most of the time, it wasn't related to issues related with either the two missions that we're talking about here. But I tell you, the three of us are sitting up here right now really excited because this is where, after all of this hard work, we really start to capture what we've all been involved with and started out to do, and that's to get the information that we're looking for. It's going to be an exciting time for the real-time events of impact for Tony, and we'll have a one-year mission for Lunar Reconnaissance Orbiter focused on exploration goals and objectives, and then an extended science mission that will continue for a few years after that, focusing on science objectives. And that's really where the payoff is getting that information back so that we get what we need to better understand the moon, and scientifically to better understand our solar system and our place in it.
If I may add something, LRO was a very fast-track mission. It was conceived only about 5 years ago. The development was done on a very fast pace as a high-priority mission. The moon is nearby. Compared to other planetary missions that typically may run a decade, from conception to implementation and return of data, starting LRO about 5 years ago and getting to this point is actually a very fast pace. We were ready to go last fall because of the certain challenges associated with the launch vehicles. We're now looking forward to a launch this week. We're eager, ready to go, and the delays are a bit frustrating, but we're just looking forward to the data.
And likewise for myself, I don't think I can say much more than very anxious to get off, get past lunar swing by, so our entire team can kind of take a sigh and take a breath. It's been, as Rich said, for LCROSS 2, a sprint from day one. Once we get by our swing by, we get into cruise, and we can take a breath until impact. What's unique about LCROSS 2 and the delays is we're using the Centaur, the actual launch vehicle, in a way that it was never designed to be used before, and so we're exceedingly appreciative of the effort and the diligence that's been put forward to make this a success. So while sometimes delays are frustrating, they're what's appropriate to make sure missions are successful. So we're just excited to be here and ready to go.
Yeah, let me add one more thing. I mean, we have the three scientists up here at the table, but I'll tell you, there is a team behind us that really are the unsung heroes for these missions. When you look at the short times that are involved for both of these missions, and you look at how capable and how flexible these teams were in being able to bring these missions ready to launch at this time, that there is a huge amount of credit that really has to go to those teams, so that we can go and get the scientific and the exploration information that NASA needs.